Environmental Geology. Module 10. Hydrogeology and Hydrologic Cycle. 1 Introduction. Air is a mixture of gases. The principal among the gases are nitrogen, 78% by volume, oxygen, 21% by volume, argon, 0.95% by volume, carbon dioxide, 0.034% by volume, and a variable amount of water vapor. The amount of water vapor in the lower range of the atmosphere can vary over a wide range from about 0.05% to almost 4% by volume. Fig 1 pie diagram showing distribution of gases in atmosphere. The water vapor present in the air is an important causative factor for the formation of mist, fog, clouds, rain or snow. The carbon dioxide plays a role in plant life and overall climate of the Earth. Presence of ozone in the atmosphere in the altitude ranging between 20 to 30 km above the Earth's surface absorbs all the ultraviolet radiation from the sun, where otherwise it would have been detrimental to plant and animal life. The atmosphere, particularly with water vapor and carbon dioxide change the incoming solar radiation, reaches both the land and ocean at the Earth's surface. With the increase in carbon dioxide content the radiation would be more and the Earth become warmer. P. R. Pisharoti, a pioneer in Indian meteorology, has in his book, Meteorology for the Indian Farmers, special publication, Indian Space Research Organization, Bengaluru, September, 1986. 4. Environmental Geology. Has comprehensively dealt about the solar radiation, its interaction with the atmosphere, structure of the atmosphere and the variations of pressure and temperature with altitude. He has outlined how horizontal pressure differences on a rotating Earth, primarily caused by temperature differences, generate winds. He also has described the physics of clouds and rain or snow. He has given an outline of different weather systems which has regional impact. Fig 2 conversion of solar radiation into heat energy. Water in the planet Earth, occurring in liquid, solid and gaseous status, displays varied degree of motion. The hydrological cycle, also known as water cycle, defines the movement of water and storage of water in Earth. Agriculture is strongly dependent upon weather. Human survival is dependent on water availability. Seasons impart a rhythm to life of the Earth. The sequence of events in hydrologic cycle appears to be simplistic. But, in reality, the hydrologic cycle is a vast and complicated cycle which involves a large number of paths of varying time scale. It is a continuous recirculating cycle. It has neither a beginning nor an end. Subramanya, 2013. 5. Environmental Geology. 2 objectives. 1. Explain stages of hydrological cycle. 2. Describes the various factors affecting hydrological cycle. 3. Narrating the importance of hydrological cycle. 4. Describes the movement and circulation of water on Earth. 3. Concept map. The components of the hydrological cycle: evaporation, condensation, precipitation, runoff. 6. Environmental Geology. Fig 3 the water cycle. 4 descriptions. 4 to 1 hydrological cycle. The hydrologic cycle begins with the evaporation of water from oceans and lakes. Evaporation is the change of water form from a liquid stage to a gaseous one. The largest movement of water in the water cycle is the evaporation of water from the oceans. Evaporation of water from the warm surface of oceanic body results in increased amount of moisture in the colder, drier air immediately above. As water vapor moves up, it gets cooled and condenses into clouds. Condensation is the change of water form from gaseous form into liquid form. Condensation occurs in atmosphere when warm air raises, cools and loses its capacity to hold water vapor. When water vapor condenses, it becomes droplets in the cloud. The upward motion that generate clouds can be the result of convection in unstable air. Convection is the result that happens when the land surface is hot, the overlying air. 7. Environmental Geology. Which warms up becomes less dense than the air in the surrounding parts and attains motion in a vertical direction. When surface winds are deflected by friction towards the center of the low-pressure surface, it would result in extratropical cyclones. Surface convergence can generate rising motion, leading into condensation of water vapor. Fig 4 hydrological cycle and distribution. The huge quantity of evaporated water, in one form or the other, moves around the globe until it returns to surfaces, precipitation. The precipitation is the primary natural mechanism of water transportation from the atmosphere to the surface of the Earth. It may include rain, hail, snow and freezing rain. While much of the clouds get back into the oceans and lakes as rain, some part of it when driven by wind onto the land, precipitate into rain, snow, hail, etc. A well-developed, extratropical cyclone can generate any or all forms of precipitation. With continued evaporation, water. 8. Environmental Geology. Vapor in the cold part of atmosphere condenses to form ice crystals. It is said that the atmosphere keeps water for an average of 9 days before it releases it down as rain. Fig 5 diagram depicting annual water budget. The boundary between air masses, front, can either be warm, cold or stationary. In case of cold front, a colder, denser air mass lifts the warm moist air ahead of it. As the air rises, it cools and the moisture in it condenses to produce clouds and precipitation. Due to steep slope of a cold front, vigorous rising motion leads to formation of showers and occasionally severe thunderstorm. In the case of warm front, the warm, less dense air lifts up the colder air ahead. Again, the air cools and its moisture condenses to form clouds. Precipitation that develops in advance of a surface warm front is typically steady and widespread than precipitation associated with a cold front. 9. Environmental geology. Fig 6 flowchart of drainage basin is an open system. Inputs into the drainage basin include energy from the sun for evaporation, precipitation, rain and snow. Outputs move moisture out of the drainage basin and include evaporation and transpiration from plants, collectively called evapotranspiration, runoff into the sea. Water percolating deep into underground stores where it can be effectively lost from the system. Stores of water. On the surface, glaciers, lakes, rivers, puddles. 10. Environmental geology. Vegetation stores water by interception and plants. The soil can hold water. Groundwater is stored in permeable rocks. Transfers and flows moves water through the system and enable inputs of water to be processed from one store to another. Transfers include through fall, stem flow, infiltration, through flow and groundwater flow. Fig 7 flowchart of water budget. While almost all the water is contained in oceans, only 3% is the fresh water available on land surface, and of that 3% almost 69% is trapped as glaciers. Glaciers can keep water trapped as ice for thousands of years. The lake effect snowfall is caused when cold wind blows across a large lake. The intensity of snowfall can get enhanced due to additional lifting of clouds in mountainous terrain. Once the snow begins to melt, the water absorbed by the ground becomes groundwater or returned to the lake, ocean as runoff. The water through precipitation, when reaches the ground, some part of it evaporates back into the atmosphere, some part gets consumed by the vegetation, and a part saturates the soil, infiltrate and percolate into ground as groundwater. The part of water consumed by vegetation reaches the atmosphere as transpiration. Groundwater may as springs and or base flow reach the path of the stream. Rest of the precipitation, as overland flow, largely finds its course into the streams and rivers as runoff. The stream river water flow ultimately gets emptied back into lakes and oceans. Thus, as Subramanya 2013 puts, the total water resources of the earth are constant and the sun is the source of energy for the hydrological cycle. The main components of the hydrologic cycle can 11. Environmental geology. Broadly be classified as transportation component and storage component. The transportation components include precipitation, evaporation, transportation, flow, infiltration and runoff. Storage components are that of storage on the land surface, like ponds, lakes, reservoirs, etc., soil moisture storage and groundwater storage. The Horton's representation of the hydrological cycle illustrates the storage and transportation components and their relative positions in the cycle. Fig 8 typical hydrological cycle in flowchart form. The hydrological cycle has an influence on agriculture, forestry, geography, etc. Human interference in the hydrological cycle, like through artificial rain, change of vegetal cover, change in land use, indiscriminate extraction of groundwater, etc., can cause serious repercussion in the fields of agriculture, forestry, geography, etc. It has its immense application in the design of projects about water supply, irrigation and drainage, flood control, coastal geomorphology and geohydrology. 4-2 El Niño. In the tropics, where weather is warm year-round, rainy seasons known as monsoons alternate with dry period. But the rhythm of the seasons cannot be relied upon. The tropical Pacific Ocean and global atmosphere disrupts normal patterns of climate and life. The alternation between the normal climate and a different recurrent set of climatic conditions in the Pacific region is called El Niño. The term, El Niño, was originally used by fishermen along the coast of Ecuador and Peru to a warm ocean current appearing around the period of Christmas over several months. 12. Environmental geology. During 1920s, Walker, who was on assignment to India, trying to find a way to predict the Asian monsoon, discovered a remarkable connection between barometer readings at eastern and western sides of the Pacific. He notified when pressure rises to the east, it usually falls low in the west and vice versa. Walker coined the term, Southern Oscillation, to the ups and downs in that east-west seesaw in Southern Pacific barometer pressures. Fig 9 typical winter time pattern, El Niño. 13. Environmental geology. Fig 10 diagram showing formation of El Niño. When the seesaw is in its high index, strongly tilted state, pressure is high on the eastern side of the Pacific and low on the western side. Along the equator, the east-west pressure contrast drives easterly, east-to-west, surface winds from the Galapagos Islands nearly all the way to Indonesia. When seesaw switches into its low index, weakly tilted state, the easterly surface winds weaken. The biggest changes in the slope of the seesaw and in the strength of the easterlies occur over the western Pacific. To understand how El Niño affects the ocean, it is necessary to learn how surface winds move water during normal years and how the resulting motions affect water temperature. The easterly winds that blow along the equator and the southeasterly winds that blow along Peru and Ecuador coasts both tend to drag the surface water along with them. The Earth's rotation then deflects the surface currents northward in the northern hemisphere and southward in the southern hemisphere. The surface waters are therefore deflected away from the equator in both directions and away from the coastline. Where the surface water moves away, colder nutrient water comes up from below to replace it, and this phenomenon is called upwelling. Both the equatorial upwelling and the coastal upwelling are concentrated in narrow regions of around 150 kilometers wide. The winds that blow along the 14. Environmental geology. Equator also affect the properties of upwelled water. In the absence of the wind, the dividing layer between the warm surface and the deep cold water called thermocline would be nearly flat, but the winds drag the surface westward, raising thermocline up to the surface in the east and depressing it in the west. The winds control the upwelling. The winds are also responsible for the cold tongue in the sea surface temperature pattern. But the resulting changes in the sea surface temperature will in turn have effects on the winds. When the easterlies are blowing at full strength, the upwelling of cold water along the equatorial Pacific chills the air above it, making it too dense to rise high enough for water vapor to condense to form clouds and rain drops. As a result, this strip of the ocean stays conspicuously free of clouds during normal years, and the rain in the equatorial belt is confined to the extreme western Pacific near Indonesia. But when the easterlies weaken and retreat eastward during the early stages of an El Niño event, the upwelling slows and the ocean warms. The moist air above the ocean also warms. It forms deep cloud, resulting in heavy rain along the equator. The change in ocean temperature thus cause major rain zone over the western Pacific to shift eastwards. Related adjustments in the atmosphere cause barometer pressure to fall over the central and eastern Pacific and rise over India, Indonesia and Australia, thereby resulting in eastward retreat of the easterlies. Thus, it is difficult to identify the subtle change in the ocean atmosphere system that initiates a transition into or out of El Niño condition. The twists between ocean and atmosphere can have ripple effect on climatic conditions in the far regions of the globe. Dense tropical clouds distort the airflow aloft, 8 to 16 kilometers above sea level, but on a horizontal scale of thousands of kilometers, the waves in the airflow in turn determine the positions of the monsoons. The impact of El Niño upon climate in high temperature latitudes show up more clearly during winter time. 5 Hydrogeology. Hydrogeology is the subject that deals with distribution and movement of groundwater in the soil and rocks of the Earth's crust. Merriam-Webster defines hydrogeology more appropriately as a branch of geology concerned with occurrence, use and functions of surface water and groundwater. Hydrogeology is the study of water contained in materials of Earth's crust, its origin, evolution, physical and chemical characteristics, and ultimate destination. The terms groundwater hydrology, geohydrology, and hydrogeology are used interchangeably. While hydrogeology is the term commonly used by geologists and hydrogeologists, the term geohydrology is most often used by 15. Environmental geology. The civil engineer. Whether it is called hydrogeology or geohydrology, the meaning remains almost equivalent. Hydrogeology is an interdisciplinary subject and deals on chemical, physical, biological, and legal aspects of surface and groundwaters. The subject of hydrogeology, apart from various science faculties like of agriculture, horticulture, soil, civil engineering, etc., has also a larger bearing on urban, forest, and coastal hydrology. Fig. 11 Interaction of hydrogeology with other geocomponents. Hydrogeological features mainly dependent upon geology, geomorphology, and climatology of an area. The rainfall distribution both in space and time, intensity, frequency, and variability is of considerable importance for understanding hydrological aspects of any given area. In a virgin unaltered landscape, after a dry rainless period when rainfall occurs, a good part of it will be lost through evaporation. Subsequent rains form part of the surface runoff. A rapid runoff would mean minimum percolation into the earth even if the rains are normal. Subsequent rains form part of the surface runoff. A rapid runoff would mean minimum percolation into the earth even if the rains are normal. Saturation runoff occurs after soil. 16. Environmental geology. Water zone is fully saturated. Infiltration of water is the downward movement of water from the ground surface. The maximum infiltration rate is the infiltration capacity, or F capacity. Surface flow in a natural landscape appears when the water availability exceeds the F capacity. Infiltration of water is distinct from percolation. The water percolation is the transit of infiltrated water by gravity through the zone of aeration to the zone of saturation. In case of hard rocks, the water percolates through weathered mantle that constitutes zone of aeration and/or fractures. The water contained in materials of Earth's crust is groundwater, and this quite often spelled by many as groundwater. When groundwater is not near to the Earth's surface, there forms a zone in where majority of open spaces are with air. This is called zone of aeration, or Vadose zone. Vadose zone, which is the zone of aeration, is the part of Earth between the zone of saturation and the ground surface. Vadose zone has a pressure head less than atmospheric pressure. The Vadose zone does not include the area that is with water content above the water table, and this is referred to as capillary fringe. The capillary fringe is the result of the process of capillary action. Movement of water within the Vadose zone involves study of soil, hydrology, and hydrogeology. Groundwater recharge under natural process occurs through Vadose zone. To put it in brief, the Vadose zone is the subsurface unsaturated or undersaturated part of the geological rock formation that lies above the groundwater table. In marshy zone, the Vadose zone may be absent. Rate of water percolation and groundwater recharge is dependent upon the rock characteristics in the Vadose zone. When there is impermeable rock in the zone of aeration, downward movement of infiltrated water gets blocked or restricted, resulting in the saturation of the interstices of the rock material above the impermeable barrier. Water in such a zone is called perched groundwater. The upper surface of the zone of saturation is the water table, or phreatic surface. In other words, the area separating the vadose zone and the phreatic zone is water table. The water table fluctuates between seasons. Some use the term phreatic zone in preference to zone of saturation. The part of the geological rock type, be it alluvium or hard rock, when the pore spaces, fracture zones in them are filled with water that is infiltrated and or percolated, forms the zone of saturation, and this zone of saturation is the one between the water table and the depth at which the rock type can no more hold and transmit water because of impermeable characteristics. In other words, the lower limit of zone of saturation extends to such depths at which the interconnected openings remain absent or negligible. 17. Environmental geology. Fig. 11 Stages of formation of groundwater. An aquifer is the rock formation or part of rock formation which yields appreciable quantity of groundwater. Every aquifer has a capacity to store water which is expressed as coefficient. The storage coefficient, which is otherwise called storability, is defined as the volume of water that can be released or taken into storage per unit surface area of the aquifer per unit change in head. In the case of water table aquifer, otherwise called unconfined aquifer, which is bound at the top by the water table, coefficient of storage is analogous to specific yield. The specific yield is the saturated part of the rock to drain water under the force of gravity. It is expressed as percentage volume of water yield by draining a saturated rock to its total volume. The specific yield of rock is complementary to the specific retention. In case of hard rocks, the intergranular space, rock matrix, and the openings like joints, fractures largely are the factors that govern the specific yield. The rock matrix, when porous and permeable, and the joints, fractures together, form double porosity characteristics. If the rock matrix is hard, massive, nonporous and not permeable, in such cases fractures, joints when are present, will act as water conduits. Rock will not be an aquifer when with its extensive spread are massive, hard, non-porous, not permeable, and fractures, joints are absent. In case of clay formations, though they are highly porous, are not permeable. The semi-confined. 18. Environmental geology. Aquifer condition prevails when the confining layer is semi-permeable. A confined aquifer is the one which will be overlaid and underlaid by impervious and impermeable rock formation. Fig. 13 Types of aquifers. Depending upon the capacity of the aquifer to accept, store and or transmit water, the rainwater and or water from any other source that infiltrates, when reaches the upper surface of the vast massive rock zone or impermeable bed, finding no scope to further percolate, gets into the process of gradually saturating all the fractures, joints and any other voids or intergranular pore space in an ascending manner. With this process on, depending upon the rate and quantity of water that infiltrate, the interconnected fractures, joints and any voids in the semi-confined, semi-unconfined and unconfined aquifer zones gradually get saturated. Groundwater recharge is dependent upon the porosity and permeability of the soil and underlying geological formation that prevails in the area. Porosity is the pore space between unconsolidated soil and other earth material, weathered and or fractured part of the rock. Permeability is the expression of the connectivity of pores to permit the water movement. This process of saturation from semi-confined to unconfined aquifer zone is possible only when the net annual draft component from the aquifer is less than the net annual groundwater recharge. Thus the unconfined aquifer, semi-unconfined aquifer and semi-unconfined aquifers which are transitionally interconnected form a composite aquifer system, more so in a hard rock terrain. Recharge to the composite aquifer system will be through the unconfined aquifer. 19. Environmental geology. When bore well taps unconfined, semi-confined aquifer, the water in the well rises to a particular level and the water level attained under such a condition is called piezometric surface. The piezometric surface or piezometric level will be dependent upon the hydrostatic pressure that sustains in the aquifer. The fluctuation in the piezometric surface is dependent on the variation in the hydrostatic pressure of groundwater within the aquifer. When the storage coefficient value S and fluctuation in piezometric surface H is known, the quantity of water added or released from the aquifer can be calculated. Darcy's experiment in 1850s led to determine the rate of flow of groundwater. Darcy's law states that the amount of groundwater discharged through a given portion of aquifer is proportional to the cross-sectional area of flow, hydraulic gradient and hydraulic conductivity. It is expressed as K equals Q AI, where Q equals quantity of water discharged in unit time. I equals total cross-sectional area through which water percolates. I equals hydraulic gradient. Fig. 14 diagram depicting Darcy's law. Permeability of a rock is its capacity to transmit water under differential pressure and is measured by the rate at which it will transmit water through a unit cross-section under unit pressure differential per unit distance. Rocks that lack porosity do not transmit water and are hence referred to as impermeable. 20. Environmental geology. Porosity thereby is not a measure of permeability. Permeability was then understood to be a field coefficient at the prevailing temperature of water. It is later the term, hydraulic conductivity, used in preference to coefficient of permeability. The capacity of a saturated rock to retain water after the drainage is specific retention. The quantity of water that will drain from a rock depends on the duration of drainage, temperature and chemical capacity of water. The specific yield is the capacity of a saturated rock to drain water under the force of gravity. It is expressed as percentage volume of water yielded by draining a saturated rock to its total volume. The groundwater resources can be categorized as dynamic reserve and static reserve. The dynamic reserve represents long-term average annual recharge under the condition of maximum use. Static reserve is the groundwater contained within the permanently saturated zone of the aquifer and that represents the total groundwater reserve minus the dynamic reserve. When the groundwater draft exceeds the normal annual replenishment and static resources are exploited in any manner, it amounts to mining of groundwater, and a time may come where it no longer is a sustainable resource. Once groundwater is contaminated, it becomes a costly issue to clean up. 3. 2.1 Introduction. Streams are the most important agents of erosion and transportation of sediments on Earth's surface. They are responsible for the creation of much of the topography that we see around us. They are also places of great beauty and tranquility, and of course, they provide much of the water that is essential to our existence. But streams are not always peaceful and soothing. During large storms and rapid snowmelts, they can become raging torrents capable of moving cars and houses and destroying roads and bridges. When they spill over their banks, they can flood huge areas, devastating populations and infrastructure. Over the past century, many of the most damaging natural disasters in India have been floods, and we can expect them to become even more severe as the climate changes. 2.2 The hydrological cycle. Water is constantly on the move. It is evaporated from the oceans, lakes, streams, the surface of the land, and plants transpiration by solar energy. Figure 2.1. It is moved through the atmosphere by winds and condenses to form clouds of water droplets or ice crystals. It comes back down as rain or snow and then flows through streams, into lakes, and eventually back to the oceans. Water on the surface and in streams and lakes infiltrates the ground to become groundwater. Groundwater slowly moves through the rock and superficial materials. Some groundwater returns to other streams and lakes, and some goes directly back to the oceans. 4. Environmental geology. Figure 2.1 Different components of the water cycle. Black or white text indicates the movement or transfer of water from one reservoir to another. Yellow text indicates the storage of water. 2.3 Stream. Meaning and concepts. A stream is a body of flowing surface water of any size, ranging from a tiny trickle to a mighty river. A drainage basin is a portion of the Earth's surface that contains a main stream and its tributaries are the area from which the water flows to form a stream. All of the precipitation, rain or snow, that falls within a drainage basin eventually flows into its stream, unless some of that water is able to cross into an adjacent drainage basin via groundwater flow. Drainage divide a ridge or strip of high ground dividing one drainage basin from another. It determines into which basin precipitation flows. The upland between tributaries is called interfluves. Figure 2.2. 5. Environmental geology. Figure 2.2 Different drainage basins. Streams within the drainage basin are either perennial or intermittent in flow. Perennial streams, permanent streams that flow all year. Intermittent stream, a stream that carries water only part of the year. 2.4 Stream order. One way of categorizing streams is by stream order. Most streams begin as springs or boggy seeps of groundwater. Some flow from lakes without an inlet. These fledgling streams are labeled first order. When a first order stream meets another first order stream, the resulting flow is a second order stream. Fig. 2.3. The second order stream picks up additional first order streams, but remains second order. Only when two second order streams meet is the result a third order stream. 6. Environmental geology. Figure 2.3 Different stream order. The study of drainage network and its characteristics of a particular region can be classified in two ways, namely descriptive approach and genetic approach. The descriptive approach includes the characteristic study of the stream forms and its pattern of a specific region, whereas the genetic approach comprises the evolution process of stream based on tectonics, lithologies, structure and topography of a region. Therefore, drainage system means the origin and development of surface runoff streams through time, and drainage pattern defines the different pattern of arrangement formed by drainage system in terms of geometrical shapes in the areas. Drainage pattern are strongly influenced by the rocks types, geological structure, climatic conditions and denudational history. Generally, the evolution of drainage system of an area is controlled by nature of initial surface and slope and geological structure. Streams and drainage system are classified into two classes based on initial slope and geological setup. 1. Sequence stream. The stream flow along the natural slope and geological fault such as consequent stream, subsequent stream, subsequent stream and resequent stream. 2. Insequent stream. The stream that do not flow along the natural slope and drain over the geological structure such as antecedent stream and superimposed stream. 3. 7. Environmental geology. 2.4.1 Sequence stream system. I. Consequent stream. Early stage of stream development and its courses in accordance with initial slope and geological fold is known as consequent stream. Figure 2.4. The consequent stream which follow the natural landscape slope are called dip stream, while stream developed along the folded structure form the master consequent stream, also called as synclinal consequent stream. The master consequent is the main stream of the drainage system of a particular consequent stream of a region. Domes and volcanic cones are favorable topography for the formation of consequent drainage system. The drainage system off the Indian coastal plains is the best example of consequent stream. There are two types of consequent stream. I. Longitudinal consequent stream which follow along the syncline or depression axis in a geological folded structure. E. Lateral consequent stream which follow from the lateral sides to join the depression axis. Thus the lateral consequent stream normally joins at almost right angle to longitudinal consequent stream. Figure 2.4 Various types of sequence stream system. 8. Environmental geology. 2. Subsequent stream drained from the anticlines or ridges axis which developed after master consequent stream and joined the main stream is called subsequent stream, figure 2.4. Generally, it defines as the transverse stream to the master consequent. For example, the Asan River and Song River are the subsequent stream which also a tributary of the Yamuna and Ganga River are again the master consequent stream. 3. Subsequent stream movement of stream current in reverse direction to the master consequent is known as subsequent stream, figure 2.4. The stream drained along the slope of landscape, thus, subsequent stream is also type of consequent. The stream developed from the northern slopes of the Himalayas ranges of east-west direction flow northward to join the tributary drain east-west direction, subsequent stream, of the southward flowing master consequent stream. For example, numerous stream originating from the Siwalik ranges flow northward due northern slopes and meet east-west subsequent stream of the southward flowing master consequent of the Ganga and Yamuna River. Thus, the tributaries flowing northward from the Siwalik ranges are the subsequent stream. IV. Resequent stream tributary, which lately developed and drained in the parallel direction to the master consequent is referred as requiescent stream. Since the stream is of recent evolution as compared with master stream, thus called requiescent, figure 2.4. The resequent stream is originated from folded geological structure during the starting of second cycle of erosion. The anticlinal ridges and synclinal valleys are converted into anticlinal valleys and synclinal ridges in due time during the first cycle of erosion in folded mountains. Thus, the longitudinal stream initiated by the end of first cycle of erosion in the anticlinal valleys and the development of new valleys in the syncline with the beginning of second cycle of erosion. Later, the stream originated in the synclinal area that flow parallel to the original longitudinal consequent form at the first cycle of erosion become resequent stream. 2.4.2 Insequent drainage system. I. Antecedent drainage system. Development of stream long before the upwarping of land surface or which antedate the upliftment of land or mountain by maintaining the constant watercourse through continuous downcutting of their valley is known as antecedent stream. 9. Environmental geology. Figure 2.5. It is important to note that river or stream do not divert or deflect pre-existing course with the subsequent uplift of the land area and further maintain the natural course by downcutting its valley at the equivalent rate with the rate of upwarping of the landmass. It is difficult to know the exact uplift rate of land as well as downcutting rate by the river in the particular area. Hence the concept of antecedent stream is totally related to both assumption and prediction. 2. The degree of upwarping is an important factor for the initiation of antecedent drainage system because stream course following the same pathways depend on local environment conditions. In such case, stream or river undergo continuous erosion of valley through active incision at the equal rate of upliftment thus able to maintain the pre-existing course. The dimension of uplift of land should be only local perspective and not the regional one for the evolution of antecedent stream. The stream originated in Himalayas regions are the examples of antecedent drainage system. Jhelum, Ganga and Yamuna River are the antecedent to the lesser and outer Siwalik ranges and Kamala, Rapti and Gola River are represent antecedent stream to only outer Siwalik range. Figure 2.5 Antecedent drainage system. 10. Environmental geology. 3. Superimposed drainage system. A river flowing on a particular geological formation and structure has inherited the characteristics of its previous form developed on upper geological formation of entirely different structural characteristics. In other words, a superimposed drainage is formed when nature and characteristics of the valleys and flow direction of a consequent stream developed on the upper geological strata underlying the lower strata of entirely different characteristics, figure 2.6. The current of consequent stream eroded the flat ground surface horizontally of bedded sedimentary rocks. With due time passage the stream excavated the underlying surface through repeated vertical erosion of the valley. Thus valley developed on the upper structure is superimposed on the lower strata and river maintains the normal flow direction and its drainage pattern in the area. The conceptual difference between superimposed and antecedent drainage system or superimposed stream developed valley in the upper geological formation and extending to lower structure irrespective of its different characteristics and without any upwarping of the landmass whereas antecedent stream maintain the previous water course in the valley besides continuous upliftment of the land area across the river pathway. Most the rivers of the Deccan Trap region of Indian Peninsula are superimposed stream due to evolution of recent drainage system on the freshly formed surface by solidification and cooling of lavas erupted during late Cretaceous and early Tertiary periods. Such stream excavation of upper lava covers and superimposed on the underlying geological structure. The Sabarnareka River is an example of superimposed stream on Dalma and Phyllite hills to the west in the southeastern Chotanagpur Plateau region of Jharkhand. 11. Environmental geology. Figure 2.6 Superimposed drainage system. 2.5 Drainage pattern. The drainage pattern defines the geometrical shapes of the stream system and the spatial array of stream in a specific area or region. The drainage pattern of a particular area is not identical with to another region which relatively depends on nature of slope, lithological and structural factors, vegetative area and environmental conditions. Generally, there are different types of drainage pattern namely, 1. Trellised pattern, 2. Dendritic pattern, 3. Rectangular pattern, 4. Centrifugal or radial pattern, 5. Centripetal pattern, 6. Annular pattern, 7. Barded pattern, 8. Pinnate pattern 9. Herringbone pattern, and 10. Fig.2.7. Parallel pattern. 12. Environmental geology. Figure 2.7 Different types of drainage pattern. I. Trellised pattern. It is formed by the array of tributaries, lateral stream and major consequent stream flowing the natural land slope and well adjusted to the geological structures, figure 2.7 I. Such drainage pattern is originated in the region having alternated parallel valleys, synclinal, and ridges, anticlinal. Numerous master consequent longitudinal streams is developed in the elongated synclinal valley, whereas lateral stream originated from both sides of the ridges and join at almost right angle to master consequent stream. Hence, the stream arrangement formed by the combination of consequent longitudinal stream and lateral consequent stream is called trellised pattern. The main difference between trellised and rectangular pattern based on the stream space between them. In the trellised pattern, the stream gaps are closed, whereas rectangular pattern is formed by the wide gaps of stream. 13. Environmental geology. 2. Dendritic pattern. This stream pattern is far most commonly developed in the area where the unconsolidated rock formation can be easily eroded in tree-shaped structure, figure 2.7e. Such dendritic pattern is independent of structural and lithological controls but associated with homogeneous lithologies. Slope and permeability of rock is the most ideal condition for the development of stream. Moreover, the stream network is more extensive in such land surface having flat surface, gentle slopes and permeable rocks. This pattern develops in different structural and lithological environments such as in the mountains, Himalayas Plateau, Deccan Plateau, Peneplain surface, Indian Peninsular, Alluvium Plain, North Indian Plain, Desert Plain, the Rajasthan Plain. 3. Rectangular pattern. It is normally originated in the land surface where numerous surface runoff, rills, along weathered and eroded rocks along the interfaces of joints, faults and fractures form rectangular pattern. These small rills increase the width and length with passage of time, become channels which drained at the lines of faults. Thus, the tributaries stream strike the master stream almost at right angles, thus form the rectangular drainage pattern, figure 2.7e. Both rectangular and trellised pattern have certain similar properties showing each tributary stream connect their master stream at right angle. But the difference between them is defined by the confluence angle is guided by strikes and dip angles of the bed rocks and narrow space tributary in trellised pattern, while rectangular pattern have the confluence angle is determined by the weak faults lines and wide streams gaps. IV. Radial pattern stream which divert away water tributary from central high point to various directions along the natural gentle slope of landmass is called radial pattern, figure 2.7 IV. Such stream also known as centrifugal pattern. The favorable land structure for the evolution of radial pattern are dome structure, volcanic cones, batholiths and laccoliths, residual hills and isolated uplands respectively. The above-mentioned land reliefs collect the water at the particular central cavity point and drained out along the slope resemble the spokes of wheel forming consequent stream. The best example of radial drainage pattern is the entire drainage array of Sri Lanka. In India, the upland area of Ranchi city located south. 14. Environmental geology. West developed numerous stream, namely, South Cole, Sabarnareka, Kanchi and Karo rivers which represent the radiate drainage pattern. V. Centripetal pattern. Another name of centripetal pattern is known as inland pattern, which is opposite to the radial pattern. Inland drainage pattern is developed in the low-lying or cone of depression area where numerous streams converge or direct towards at a particular region forming water accumulating zone or a basin, figure 2.7b. A series of stream that originated from surrounding elevated land surface come together at a specific low central area which may be a basin or Carter Lake. The central low-lying area at the top of Raiagar Dome in the Lower Chambal Basin is the example of centripetal drainage pattern. V. Annular pattern. Tributaries of master consequent stream are initiated in the circular shape is called annular pattern. The other term of annular pattern is known as circular pattern. Such pattern has appeared in the area characterized by a mature and dissected dome mountain having parallel and alternate group of soft and hard rock beds. The different rate of erosion of soft and hard rocks produce ringed structure with resistant hard rock strike outward and less resistant soft rock form circular fissure, figure 2.7b. The master consequent stream develop at the dome diverse down the slope like radial drainage pattern and the tributary streams developed by the soft bed erosion have arcuate shape finally meet again the master consequent stream, thus form the annular drainage pattern. An example of annular drainage pattern is the dissected Sonapet dome of Uttaranchal. 7. Barbed pattern. It is rare kind of stream pattern generally formed due to river capture. Barbed pattern is developed when the tributaries flow in opposite direction and join the master stream in hook-shaped bend, figure 2.7b. 8. Pinnate pattern. Pinnate stream similar the feature of leaf veins. Such pattern is formed when master stream is developed at the narrow valley and their tributaries from the steep sides of parallel ridges meets the longitudinal main stream at acute angle, figure 2.7b. The Upper Sun and Narmada River network represent pinnate drainage pattern. Ix. Herringbone pattern. The term herringbone is derived from the bone pattern of herring fish. Such drainage pattern is known as rib pattern, figure 2.7 Ix. It is developed in the Board Valley mountainous area which is flanked by steep slopes of parallel ridges. The master. 15. Environmental geology. Stream occupies the longitudinal valley and the lateral consequent tributaries develop from the parallel ridges join the longitudinal consequent stream almost at right angle. The upper Jhelum River in the Kashmir Vale feeds by numerous tributaries from the both sides is an example of herringbone drainage pattern. X. Parallel pattern. It is characterized by numerous stream flowing along the regional slope and parallel to each other, figure 2.7x. Such type of drainage pattern is commonly occurred in continuous uniform slope and sinking rock beds like newly emerged coastal plains. The stream originated from the ridges of Western Ghat drained along the slope and maintained their water course towards west to feeds the Arabian Sea. Similarly, the eastern coastal plains of India also formed parallel drainage network. 2.6 Flood. Meaning and concepts. Flood, an event during which the volume of water in a stream, river exceeds the stream's normal limits. Runoff, water that flows on the land's surface. About 10% of Earth's water as runoff. Flooding occurs when a river's discharge exceeds its channel's volume, causing the river to overflow onto the area surrounding the channel known as the floodplain. The increase in discharge can be triggered by several events. The most common cause of flooding is prolonged rainfall. If it rains for a long time, the ground will become saturated and the soil will no longer be able to If it rains for a long time, the ground will become saturated and the soil will no longer be able to store water, leading to increased surface runoff. Rainwater will enter the river much faster than it would if the ground wasn't saturated, leading to higher discharge levels and floods. As well as prolonged rainfall, brief periods of heavy rain can also lead to floods. If there's a sudden burst of heavy rain, the rainwater won't be able to infiltrate fast enough and the water will instead enter the river via surface runoff. This leads to a sudden and large increase in the river's discharge, which can result in a flash flood. Although many floods are triggered directly by precipitation just a few hours after it falls, some floods can be triggered by precipitation that fell many months ago. Precipitation that falls as snow can remain as snow on the ground until it melts. This mightn't be until the end of winter, so potentially several months. When the snow does melt, large volumes of meltwater will enter the 16. Environmental geology. River increasing its discharge and triggering floods. These floods are often annual, occurring every year when snow melts in the spring. In Bangladesh, for example, melting snow in the Himalayas triggers annual floods in the summer. Flash floods can also be triggered by slightly more catastrophic events. Erupting volcanoes can trigger very large flash floods called jokulaups when glaciers are partially or even fully melted by an erupting volcano or some other form of geothermal activity. The meltwater can enter rivers and greatly increase the river's discharge, leading to a flood. Factors that influence runoff. Topography. Soil and bedrock. Land use. Floods in major cities, especially during rainy season, are proving to disastrous not only to the environment but also have serious implications for human life and property. 2.7 Urbanization and flash floods. Floods may be normal natural events, but urbanization causes fast flooding events called flash floods, to be more likely. Figure 2.8. In a natural setting, rainwater can infiltrate into the ground and vegetation will slow sheetwash. In highly urbanized settings, rainwater cannot infiltrate asphalt and cement and there may be little or no vegetation to slow sheetwash. As a result, the increased discharge in rivers lasts a shorter time, but increases faster and by a larger amount. Figure 2.8. 17. Environmental geology. Figure 2.8. Occurrence of floods before and after urbanization. Streams are the main sources of water for human consumption, agriculture and industrial needs. Streams are the cheapest means for goods transportation, hydroenergy and disposal of wastes. Flooding is a natural geological phenomenon due to continuous hydrological cycle in the earth and changing environment. However, the increased magnitudes of flood in present scenario are related to change in land use pattern, deforestation, urbanization and human encroachment resulting modification of stream hydrology. Flood is the most common and costly types of natural and human-induced disasters. Floods occur when high amount of stream discharge to be accommodated in the normal stream channel. When the water flow is high, the stream widens its channel by overflowing its banks and submerge the adjoining low-lying area. Such low-lying flooded areas are known as floodplains. In developing country like India, human casualties from flood due to lack of proper flood control and technical emergency response to flood-affected area, absence of abating zoning regulations, high population density and lack of pre-warning system. Whereas the loss of life in developed countries is normally lower because of well-preparedness of flood disaster management and early warning system. The disruption of life, property damage and economic loss is still facing in such countries. 2.8 Causes of floods. There are many factors responsible for causing flood in the area. They are Basic causes. High amount of stream flow beyond the carrying capacity of the channel and overflow from the bank to the surrounding floodplains causes floods. The two key reasons. 18. Environmental geology. Responsible for the occurrence of floods are excess water flow from the stream catchment area or basin and deposition of sediments resulting reduced water carrying capacity of the stream. 2. Excess flow rainfall and cloudburst, melting of large ice blocks or snow resulting of dam breakage and bursting of man-made or landslide-built dams are the responsible for releasing excess flow in particular stream. 3. Carrying capacity of river. The maximum amount of water the stream could hold in a confined channel stretch is called carrying capacity of river. With the passage of time, every channel capacity is reduced to accommodate water due to accumulation of sediments carried down from the erosion of catchment basin, landslide debris, deposition of earth material for bridges construction and human settlement, industrial development and other activities obstruction the floodway. IV. Runoff versus infiltration. Flood stream discharge depends on the amount of surface runoff or the recharge flow of groundwater from rainwater. The surface runoff is determined by the percolating water into the soil strata, green vegetative cover, soil texture and nature of land slope and geological conditions. Extensive green covers and permeable soil or rocks act as catalyst in absorbing rainwater in considerable proportions, thus slow down the rate of water flow down the slope. When the precipitation rate is higher than infiltration potential of the soil cause excess surface runoff contributing stream flood. On the other hand, permeable soil have better percolating capacity of water, increases water table during monsoon season and give rise to numerous springs and seepages at foothills or down the slope, thus help in recharging stream during non-monsoon season. The rapid unplanned urbanization led to construction of building, paving and asphalted road construction has reduced the water infiltration and increased surface runoff in large cities like Delhi, Kolkata, Chennai, Bangalore and Mumbai, causing urban floods. Stream sedimentation and changing of river course. If suspended sediment load carried by stream water is managed by the formula that directly depend on, if the stream velocity becomes double, then the sediment transportation would increase 64 times. The equation for sediment transport of sandy bed rivers is GS alpha QX. 19. Environmental geology, where GS equals sediment discharge per unit width of the channel and Q equals stream discharge per unit width of the channel and X equals the exponent range from 2 to 3. Is defined as the sediment amount drained by the river that is eroded from its catchment area and channel banks. The huge amount of sediment carried by floodwater caused siltation of floodplain. The sediment debris collected from mining and road construction, deforested and wasteland area and landslides are deficient of organic nutrients spread on the floodplain, affecting agricultural productivity. Table 2.1 illustrates both natural and man-made factors leading to causes the floods. Table 2.1 Main causes of floods. 2.9 Flood hazard in India. Mountain barrier and rainfall. Indo-Gangetic plains received heavy precipitation and caused huge economic loss and human life due to barrier of the Great Himalaya Mountain, figure 2.9. The moisture-laden clouds from the Bay of Bengal moving northwards are blocked by the high mountain of Himalaya, causing torrential rainfall in the foothills and Great Indian Plain. Similarly, the Nilgiri Anamudi act as barrier for rain clouds and responsible for massive rainfall in Kerala and the Sahyadri Range in Western Ghat, figure 2.9 and 2.10. 20. Environmental geology. 2. Brahmaputra Basin being the largest basin in India's river received frequent flood due substantial change in stream hydrology related to natural disaster and unplanned development in highly earthquake-sensitive area, figure 2.9. Such factors accelerated the sediment deposition and forced the Brahmaputra currents to flow southwards, causing continuous erosion along the south bank. 3. Flood in western India. Dryland Indian states of western region, namely Rajasthan and parts of Gujarat, are characterized as desert areas with an annual average rainfall of 15 centimeters, have catastrophic floods even through erratic and localized scope, figure 2.9. Such unwanted events may be due to lack of proper drainage system and green covers, unable to channelize the excess water from sudden cloudburst in the region. In other words, floods in the desert area are direct consequence of excessive runoff and underdeveloped proper drainage system. IV. Flood frequency. India receives an average annual rainfall equivalent to about 4,000 billion cubic meters (BCM). This only source of water is unevenly distributed both spatially as well as temporally. The estimated precipitation during the monsoon season, June to September, is of the order of 3,000 BCM. Approximately 75% rainfall during monsoon period caused flood due to excess water discharge, more carrying capacity of river and stream channels. However, rainfall data from Meteorological Department shows no variation in precipitation level in the last 100 years, but flood frequency and their intensity have been increasing. Such increased in flood frequency may be attributed to deforestation, unplanned urbanization, change in stream hydrology, siltation of stream channels and geological disaster. Flood frequency of any river is calculated from the relations curve of a particular stream discharge and flood recurrence intervals in years. 21. Environmental geology. Figure 2.9 Flood hazard zone in India. Source. Accessed, the 20th of June 2017. 22. Environmental geology. Fig. 2.10 Flood-prone area in India. 2.10 Management of floods. The flood management required strategies to regulate the excess water flow suddenly and intensely in the drainage network. The main objectives for flood management are to reduce the surface runoff by enhancing infiltration, channelizing excess water and spread through canals and streams. There are different measures that may be adopted for controlling flood, namely, watershed treatment. Proper watershed management is one of the vital methods for flood control in downstream floodplain. It involves reduced surface runoff by increasing water infiltration rate, wherein depend on the permeability and porosity of soil, degree of slope, vegetative cover and humus-rich soil. Catchment afforestation and plant litters decrease water movement during monsoon seasons and enhance recharge of groundwater. Further, terracing and strip cropping also enhance infiltration and reduce the amount of flood runoff. 2. Reservoirs and detention basins. The construction of reservoirs and detention basins is to reduce flood discharges in rivers by developing small check dams and large major dams. Numerous check dams stands in stream tributaries would minimize flood hazards both at the sub-basins and finally at the main river. Surface water storage structures on foothills like community ponds, tanks and reservoirs should be used to harvest water to prevent excess water flow in river or streams, an alternative water source for dry seasons. There are many natural water bodies available in floodplain, namely, wetland, marshes, moors and mangroves that serve as water regulating reservoirs, enable to store huge amount water during excess surface runoff and again release water during dry season, feeding nearby natural stream. 3. Water spreading. Stream flood water can be directed or evenly distributed through barren and abandoned land, agricultural field like paddy area and desert drylands where some volume of water will be infiltrate in the subsurface strata and lost as evaporation. Likewise, flood water discharge can be spread in marshes, wetlands, lakes and mangroves. 23. Environmental geology. IV. Recharge of groundwater. Groundwater is the main source of drinking, agricultural and industrial purposes. Both natural and artificial recharge of groundwater through excess water can be effective methods for flood abate and conservation of water. River, stream, lake and ponds does natural recharge of groundwater and artificial recharge are carried out by constructing artificial recharge structure through recharge tranches and dugwell. V-stream channelization. A series of canal network can be useful measures for reducing flood hazards. Thus it requires proper channel improvements by deepening, widening, straightening, lining of channel beds and its banks and clearing of vegetation and debris to increaseth carrying capacity of rivers. On the other hand, channelization has numerous environment problems like disruption of stream ecology and equilibrium between rate of erosion, sediment deposition and water flow rate. Change in the stream velocity can lead to reduction of biological productivity. Sometimes upstream channelization may increase flood hazard downstream due to rapid drain of floodwater downstream than the lower stream discharge water and coincide of flood peaks for both tributaries and main river. Thus flood management program must aware these factors while channelizing a particular stream. V. Flood embankment. The most commonly adopted practices for flood management in India to prevent excessive water spillage by constructing bunds or embankment parallel to the river banks. Artificial land filling of the river bank is another way of preventing spillage of high water flow to the surrounding flood-prone area and a very costly measure. Figure 2.11. 24. Environmental geology. Figure 2.11. Artificial bunding of river bank. 7. Hazards mapping and land use regulation. Flood management planning requires information of floodplains to identify the floodways in relation to land use. This map shows I. Areas or belts that are recurrently inundated, E. Areas where construction cannot be permitted, and E. Areas where recharge of groundwater is taking place in order that no polluted floodwater is allowed to infiltrate. The floodplain demarcated must free from human development and construction activities and limited agricultural practices. If necessary, direction from legislative measures to restrict and cut off engineering, industrial and economic activities in these zones. The flood-prone areas are strictly identified by studying past flood occurrences and the natural water regime of the river. 8. Flood forecasting and warning. Forecasting flood and timely warning to the people of vulnerable areas, relief agencies and quick response team is an essential system of rational flood management. The development of effective network of warning system requires the following prerequisite monitoring like I. The amount of rainwater, E. The volume of discharge and flow velocity, E. Flood, depth of flooding and IV. The duration of inundation and the area likely to be inundated. Table 2.2 shows the lists of the flood forecasting stations in India. 25. Environmental geology. Table 2.2. List of flood forecasting. (29) Environmental geology. 2.12 Summary. In the present chapter an attempt has been made to provide the complete details on the streams and floods. Streams are responsible for the creation of much of the topography. They are also places of great beauty and tranquility, and they provide much of the water that is essential to our existence. But, during large storms and rapid snowmelts, they can become raging torrents capable of moving cars and houses and destroying roads and bridges. When they spill over their banks, they can flood huge areas, devastating populations and infrastructure. Flooding is a natural process caused by heavy rains and snowmelt. India, generally floods occur during the 4 monsoon months of June to September. According to the various causes, floods are of various types like flash floods, single event floods, coastal floods, floods caused by dam failures and estuarine floods, etc. In view of the severe impact of floods on human society, many serious attempts have been made worldwide, including India, to improve the scientific understanding of the flood phenomenon. In India, where floods are major annual events of great hydrologic and geomorphic significance, the numbers of case studies are surprisingly limited. A paradigm shift is necessary from the current emphasis on flood control to flood management. It must be realized that floods are a part of the natural river process. They become a hazard when human interference with river dynamics causes unwanted inundation and consequent loss of life and property. The case histories described in this narration illustrate that the boundaries of a major river basin cut across interstate and international boundaries. There have been success stories and hopefully more will follow. But the fact remains that 1/8 of India's geographical area is flood-prone. Therefore, it is important that the management options presented in this chapter are considered at the highest level and an action plan is put in place. While we can never contract with the future or accurately predict all of the consequences of our actions and policies, policymakers must extend their thinking about their impacts and the impacts of private entities beyond the local, the near term, the likely, and the recently newsworthy. 30. Environmental geology. 22. Environmental geology. Fig.2.10 Flood 2.10 Management of floods. The flood management required strategies to regulate the excess water flow suddenly and intensely in the drainage network. The main objectives for flood management are to reduce the surface runoff by enhancing infiltration, channelizing excess water and spread through canals and streams. There are different measures that may be adopted for controlling flood, namely, watershed treatment. Proper watershed management is one of the vital methods for flood control in downstream floodplain. It involves reduced surface runoff by increasing water infiltration rate, wherein depend on the permeability and porosity of soil, degree of slope, vegetative cover and humus-rich soil. Catchment afforestation and plant litters decrease water movement during monsoon seasons and enhance recharge of groundwater. Further, terracing and strip cropping also enhance infiltration and reduce the amount of flood runoff. 2. Reservoirs and detention basins. The construction of reservoirs and detention basins is to reduce flood discharges in rivers by developing small check dams and large major dams. Numerous check dams stands in stream tributaries would minimize flood hazards both at the sub-basins and finally at the main river. Surface water storage structures on foothills like community ponds, tanks and reservoirs should be used to harvest water to prevent excess water flow in river or streams, an alternative water source for dry seasons. There are many natural water bodies available in floodplain, namely, wetland, marshes, moors and mangroves that serve as water regulating reservoirs able to store huge amount water during excess surface runoff and again release water during dry season feeding nearby natural stream. 3. Water spreading. Stream flood water can be directed or evenly distributed through barren and abandoned land, agricultural field like paddy area and desert drylands where some volume of water will be infiltrate in the subsurface strata and lost as evaporation. Likewise, flood water discharge can be spread in marshes, wetlands, lakes and mangroves. 23. Environmental geology. IV. Recharge of groundwater. Groundwater is the main source of drinking, agricultural and industrial purposes. Both natural and artificial recharge of groundwater through excess water can be effective methods for flood abate and conservation of water. River, stream, lake and ponds does natural recharge of groundwater and artificial recharge are carried out by constructing artificial recharge structure through recharge tranches and dugwell. Stream channelization. A series of canal network can be useful measures for reducing flood hazards. Thus it requires proper channel improvements by deepening, widening, straightening, lining of channel beds and its banks and clearing of vegetation and debris to increase the carrying capacity of rivers. On the other hand, channelization has numerous environment problems like disruption of stream ecology and equilibrium between rate of erosion, sediment deposition and water flow rate. Change in the stream velocity can lead to reduction of biological productivity. Sometimes upstream channelization may increase flood hazard downstream due to rapid drain of floodwater downstream than the lower stream discharge water and coincide of flood peaks for both tributaries and main river. Thus flood management program must aware these factors while channelizing a particular stream. B. Flood embankment. The most commonly adopted practices for flood management in India to prevent excessive water spillage by constructing bunds or embankment parallel to the river banks. Artificial land filling of the riverbank is another way of preventing spillage of high water flow to the surrounding flood-prone area and a very costly measure, figure 2.11. 24. Environmental geology. Figure 2.11 Artificial bunding of riverbank. 7. Hazards mapping and land use regulation. Flood management planning requires information of floodplains to identify the floodways in relation to land use. This map shows I. Areas or belts that are recurrently inundated, E. Areas where construction cannot be permitted, and E. Areas where recharge of groundwater is taking place in order that no polluted floodwater is allowed to infiltrate. The floodplain demarcated must free from human development and construction activities and limited agricultural practices. If necessary, direction from legislative measures to restrict and cut off engineering, industrial and economic activities in these zones. The flood-prone areas are strictly identified by studying past flood occurrences and the natural water regime of the river. 8. Flood forecasting and warning. Forecasting flood and timely warning to the people of vulnerable areas, relief agencies and quick response team is an essential system of rational flood management. The development of effective network of warning system requires the following prerequisite monitoring like I. The amount of rainwater, E. The volume of discharge and flow velocity, E. Flood height, depth of flooding and IV. The duration of inundation and the area likely to be inundated. Table 2.2 shows the lists of the flood forecasting stations in India. 25. Environmental geology.